This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions about software engineering topics at least once a month. Thanks to our audience and the partners listed on our website for supporting the podcast. Hello, welcome to SE Radio. This is an episode that is a little bit different than some of the others we've done before because it's a little bit off topic, but it's still close to what we were talking about usually, which is obviously computer and software. This one is more about hardware. It's specifically about chip production, chip manufacturing, with a focus on the wafer scanners that are used to project the structures of the chip onto the wafer. I recently had the chance to, well, not so recently, I had the chance to talk to people at ASML. They manufacture these wafer scanners in Eindhoven in the Netherlands. And this is the result of this conversation. It's an interview with Wilbert Albers, who is a software engineer at this company. This episode has been previously published in Omega Tau, my other podcast on science topics. So if you've listened to that, you probably want to skip this episode. It's the same content, but as I know from the statistics, most people who listen to SE Radio don't listen to Omega Tau, so we thought we'd kind of cross-publish it here because it really affects both communities. If you like this kind of stuff, you probably want to subscribe to Omega Tau in the future, but we thought we'd bring you this one on the SE Radio channel as well. So, as I like to say on Omega Tau, as usual, we start with our guest introducing himself so you know who he is.
Well, I'm Wilbert Albers. I'm a software engineer at ASML, and I am already quite some time at ASML. I started here in 1998 just as a coding guy for a subsystem we call Radical Stage. Mm-hmm. And then I got into architecture. I got involved into the software architecture of a synchronization control component, because synchronizing various subsystems is a very important aspect in our Waferscanner. And later on I also got involved into the architecture of a specific wavefront aberration sensor.
Okay, we'll have to talk about that later, I guess.
But in general it was in the last 10 years a lot of architecture, and from getting very specific to more and more generic stuff. Yeah. So that's the time being.
So ASML, by the way, do the letters ASML stand for anything?
If I'm right, they are for Advanced Semiconducting Manufacturing Lithography.
Ah, okay, good. Which introduces the topic. We're going to talk about chip production and specifically wafer scanners, which are the lithography machines that put the chip layout, well, we talk about that, onto the chip. So I guess before we talk about chip production, maybe a quick overview about what a wafer scanner does, and what your company does in this space.
In order to make chips, you need to be able to project a very detailed image on a very small surface, and that projection is done with a device called a wafer scanner. So we have a light source, we have a mask containing the pattern that needs to be projected, we have a piece of optics, a lens, and then we have a substrate, which is the wafer, which will be receiving the pattern. Obviously, in order to make some sense, this wafer has to be coated with some photoresist up front.
Talk about that later, of course. So in some sense, the wafer scanners are, if you will, the core of chip production, because a lot of the other stuff is mechanical/chemical, and this is, this puts the chip's structures onto the silicon.
Definitely, and what makes it a different kind of equipment with regard to the rest is that a lot of the other processes, I think all other processes are done on a wafer as a whole, and our scanner is doing them chip by chip, which emphasizes the requirements that we have with respect to throughput. Right. Because if the rest gets a little bit faster, we have to get a lot faster per die.
Yeah. Okay, so we'll get back to that later. ASML is a vendor of these machines. Maybe you want to talk a little bit about the company so people know who we're talking to, kind of.
Yeah, we at ASML are a company of an order of 7,000 people, situated in Veldhoven, although most of our customers are in Asia. So we have a larger support organization in Asia, and also a department in America. We design the systems definitely ourselves. the optics in close cooperation with Zeiss in Germany. Although manufacturing of the thing is for larger part outsourced to a lot of companies, especially obviously here in the region of Eindhoven. We put a thing together here at Veldhoven, then customers come, do some testing and agree to buy the thing, and then we take it down again and ship it to our customers.
So it's shipped in parts.
It's definitely shipped in parts, yeah.
Okay, so let's talk about the general process of chip production first, and then we're going to, delve deeper in the wafer scanner aspect of it. I guess to set the stage, chips are what powers computers, phones, and as I understood, increasingly memory is also a big market. So maybe we can talk a little bit about how a chip looks. What is a chip? So we know what we are building in this episode.
Well, I know that when I broke up my first television set, I noticed there were a lot of discrete components in it. And when I opened one later revision, there was those printed circuit boards. And they contained those black box, and that was where it stopped because there were a lot of pins in it, and there was going on a lot of magic in it, and you could not make any sense out of it anymore. So those are the chips, and where it starts with is really a big layer of a big disc of silicon. Yeah, we call that a wafer, and a wafer is going to hold a lot of those chips.
So how big are chips? If you look at the, I don't know, Pentium CPU or whatever they're called these days.
Well, you should look to your little pinky and look to the nail of your little pinky. That's the size of a typical chip.
Okay. And how many transistors roughly? I mean, the transistors are the core building blocks.
Definitely, yeah.
Right.
The interconnection of those make up the function of the chip. And there are billions of transistors on a chip. Really, they are incredibly small.
Any numbers? I mean, how small are, I don't know, the connections? How thin are the connectors, the connecting?
In our systems, we are faced with requirements like overlay and critical dimension. And the critical dimension is the smallest structure we illuminate. And this is in the order of tens of nanometers. So that's 10 to the power of minus 9 or minus 10.
Yeah. So before we look at the production, the transistors are the basic building blocks, and I assume that some people listening to this episode know what a transistor is. Others probably don't. I should know it because I studied physics at some point, but I'm not sure I'm still really sure about it. So what is a transistor?
Well, in fact, it's just a switch. So that means that we have 3 important points on this transistor. You need to have 2 points that need to be connected or need to be disconnected, depending on the state of the switch. And you need to have a lever, which enables you to switch. So those 3 connection points in MOS technology are called the source, the drain, and the gate.
The gate is the one that switches.
Definitely, yeah, that's the lever. So these points need to be identified in a transistor. And we make a lot of them in the very bottom layer of the silicon disk on this wafer. And the way they are connected determines the function of the chip.
And how does it work on a physical level? I mean, how is the switching? What's done there?
What is done is that the silicon substrate as such does not conduct. So it's a resistor. And by contaminating it with certain materials which are having an electron in surplus or lacking just one electron, you can make this silicon substrate semi-conducting. And then by applying a current, you get a field into the substrate, which makes the whole area between the source and the drain conducting or not, which enables you to switch.
So in other words, the purpose of producing these transistors that are part of a chip is to, first of all, inject these contaminations.
Yeah, that's where we start with.
Right, and then to identify or build the microscopic structures which identify these 3 points so you can connect other stuff to, and then putting all the connecting lines onto the chip.
In fact, only the lowest layer, because chips are built in layers, only the lowest layers hold the transistors, and the rest of it only connects them in certain ways. And obviously you cannot make all connections in one layer, because then you would have a lot of contacts that you wouldn't want to. So you have to stack them.
These layers are like bridges and tunnels.
Yeah, definitely. Yeah. There are some on the internet. You can find some pictures of such a chip. You can really see those 3D structures.
Okay, I guess we'll put some of these pictures into the show notes as links. So is it fair to say that the intellectual I should say it differently. The functionality of the chip is not in the transistors. It's in the connections between the transistors.
Yeah, that's true.
So the problem, if you build different transistors for different application purposes, then maybe the transistor structure is always the same. It's always transistors organized maybe in a grid or something, and then the trick is in the connections.
It is done like that, although for different purposes, different kind of transistors can be made.
Okay.
Being either very efficient with regard to power consumption or very fast.
Yeah, okay, makes sense. But the trick is in the connections.
Yeah, oh, definitely. Yeah.
Okay, good. And we already talked about the fact that how many layers are there typically?
It's about in the order of 20 or 30 layers.
Okay.
Yeah.
And I guess that's where this precision comes from, because if the layer 18 doesn't connect to the right pin that comes from one of these points in one of the transistors, then you're lost.
Yeah, you making a short circuit, and you get a lot of frustration when you have such a chip in your computer. Because, hopefully it doesn't work at all, but maybe sometimes it works a little bit.
Yeah.
That's even worse.
Yes. Yeah. So, and it's used for, maybe that's also something I didn't know before, that the growth for you and your customers today is not so much in processors, but also in memory.
Oh, yeah. A lot of our customers are memory customers. In fact, their roadmap is a little bit more aggressive than the logic, as we call them.
Mm-hmm.
The logic is a real intelligent thing like the Intel and the AMD's microprocessors are doing. As memory is more regular, we can shrink more efficiently. We can tune the process more efficiently towards memory and make them in that way. They more aggressive and faster progressing in technology.
Mm-hmm. Okay. Just to clarify what we're going to talk about in this episode, we're not going to talk about chip design, like how do you do the connections in order to build an Intel Itanium processor and to have all these fancy things with branch prediction and stuff. That's not what we're talking about. We're talking about the more or less physical production of the processor after it has been designed.
Yes.
And I think that's a good separation, because today what we have in the industry is that chip manufacturing is often separated from, I think they're called foundries, who actually they program the chip, right?
Yeah, I know of companies like where Linus Torvalds had been working, Transmedia or something like that.
Yeah, and also
they really got into outsourcing their production to a company that made the physical chips for them.
Yeah, I heard that that's also relatively typical in the industry.
Yeah.
So let's talk about chip production, and I guess again this can be separated into at least two stages. One deals with the wafer and one deals with the chip. So maybe you should define what a wafer is first.
Yeah, well, a wafer is a disc of silicon, a little bit more than 1 millimeter thick, and they have become in various sizes. They used to be even smaller than 200 millimeters, but 200 millimeters was a typical size, and with
the diameter of 200.
The diameter, yes, exactly.
Okay.
And now we are working mostly with 300 millimeter wafers.
Mm-hmm.
And the reason for getting bigger in wafer size is that a lot of steps during the production are done on a wafer basis, and then it doesn't make sense whether you are just coating or processing one 200 millimeter disc or 300 millimeter
the
disc.
handling is the same,
it's
but you get more out of it.
But you get definitely more out of it, a lot of more out of it.
Yeah. So where does the wafer come from? I mean, I know that silicon is basically sand.
Yeah, they melt the sand, and then they grow out a crystal out of it. One big regular crystal. It gets a real cone of silicon, and then they make slices of it.
Okay.
And such a
cut
slice,
it down, basically.
they cut it down, and then such a slice is a wafer.
Why is it important that it's grown? Does it have to be very regular?
If it wouldn't be a mono crystal, the yield of the successful chips that can be made of it decreases due to the imperfections of that crystal.
Okay.
And then transistors don't just switch proper anymore.
Mm-hmm. Okay, I see. So the quality of the silicon wafer is important for the functioning of the chip later. Mm.
Yeah.
Okay, so we have the big cone of silicon. We cut it down, and I guess it's a challenge to not destroy the whole surface when you cut it. I guess.
Well, I don't know how they do it.
Yeah.
Even that is a big challenge.
Yeah.
But let's face it, in the end, you have to cut it down in smaller pieces, and then you have to even cut it down without destroying the rest of the chips.
How do you do that?
Well, I've seen one movie out of that. They have a saw with a circular motion going over this wafer, and obviously you have to be very with the position of that saw in order to go just between the chips. And they have to put it in water, I think, just to make it very smooth.
So that's not part of a wafer scanner?
No, that's not part. That's after the wafer has been scanned a lot of times.
Yeah. Okay, so we now have the wafers.
Yeah.
And next step is...
Well, the transistor should go in the bottom layer. And that means that the silicon, as we got into the introduction, is insulating. So we have to contaminate it at very specific spots. Spots that will make up the transistor connection points later on. So what we do with it is that we start to coat the whole wafer with a drop of photoresist, and then we spin the wafer. So the whole wafer gets coated with a nice layer of photoresist.
Photoresist is what?
A chemical fluid, which is reacting on illumination of a light with a certain wavelength.
So when you light the photoresistant, what happens?
Well, the properties of the illuminated areas change in such way that we can develop the photoresist just like an old photograph, and then we can etch away the areas that have been illuminated or the areas just that have not been illuminated.
Okay.
So and then what we end up with is a wafer where certain parts are covered still with photoresist, and other parts the photoresist has been etched away, so we are looking on the bare silicon again. And when we have such a wafer where those holes are punched into it with the photoresist, we can contaminate that area precisely with these materials that have the contaminating nature.
So the whole point of this photoresist is to basically put a mask onto the silicon with holes in it?
Yeah.
And these holes are then used as the places where the silicon is contaminated?
Exactly, yeah.
Okay, so the purpose of the wafer scanners is
making the
illumination,
image, illuminating the photoresist with the pattern.
Okay, I see.
Showing the holes, especially in the first layer.
Okay.
In later layers, different patterns are used because then we are not making the holes but connections between those holes.
Well, then the patterns are then lines instead of dots. But your machines, the wafer scanners, are used in all these layers.
Oh yeah.
Okay. So we're going to talk about the wafer scanners later in detail. But so once we have the lowest layer with the transistors, and once we've done the etching, so we have done the contamination. I mean, how do you put additional layers on top of it? You have to insulate, I guess?
Yeah, an insulator will be come in between, and also then that insulating layer will be coated with photoresist. Again, we're going to etch away those areas that we need to bring on top again, and then we are going to coat it not with a resistant layer but with a conductive layer like aluminum or copper. And then we're going to etch the top surface away, but where the holes were, those holes get filled with a little stack of aluminum.
So that gives you the vertical connection.
That gives me the vertical connection, exactly.
Okay.
Well, then you can imagine that this process gets repeated each time after each other.
Right.
And you can also imagine that it is very important to be right on spot for the next layer.
Yeah. Otherwise, the vertical connections obviously don't touch anything sensible down there.
Yeah.
Okay. So during chip production, is there a way how you can do any kind of, quality control? I mean, if you're building 18 layers, do you know that the 7th of them has been correctly built, or can you only do a black box test of the whole chip once it's finished?
I do not know whether we are capable of testing the function of the chip at an early stage, but I do know that we are capable of measuring the quality of certain illuminated structures. So you have some ways to do some intermediate measurements, but I don't know whether they are done on a regular scale. If you are in control of your process, that you just continue going on and then in the end do the black box measurement and throw away the chips that don't work.
Well, it's correct by construction versus testing, right? I mean, if you're sure that your machines are, correctly positioned and everything is great because you've verified that somehow before, then you don't have to do testing.
And obviously a lot of testing and then measuring and then tuning of those processes are like how much photoresist is needed, how long should it be illuminated, how long should the etching be done. Well, that is obviously done up front on a smaller scale.
Right, I guess you spend years optimizing these machines before they're kind of sold to customers.
I don't know because, well, it is very important for customers to be first in the market before their competitors.
Mm-hmm.
So there's always a time pressure, I think.
Yeah, this whole production stuff is also happening in a clean room environment, right?
Yeah.
So also the whole machine building, I guess, has to happen in a building your wafer scanners has to happen in a clean room environment.
We have a clean room. The clean room environment is a very, very clean environment because any particles that are flying around over there, when they enter our machine, they might end up at a wafer, which gives you a malfunctioning chip. But it might even be worse when they end up on the mask holding the pattern, because a particle that ends up on the mask will be projected in every chip on the wafer. So then you have no good chips out of it.
Yeah.
It's a very interesting environment. The people are all wearing the same dress, and sometimes, especially for the next generation systems, they are wearing mouth caps. So I know that I've seen people and worked with them a day, and I might not recognize you when they in the restaurant not wearing the suit.
Yeah. Okay, so let's look at and then of course there is one more step in the production, and that is obviously cutting, as we talked about before, cutting the finished chips down cutting the wafers down into separate chips.
Yeah, and then they need to be put into those little black houses.
Yeah.
And then they have the pins of the outside of those houses have to be connected with or called bonding, bonded with the inside connection points on the silicon die.
How many connectors does a chip have today? Typically it's in the hundreds, right?
It's hundreds, yeah.
When
you turn upside down a Pentium chip or an AMD chip, you see a lot of connection points.
Right. Yeah, when I was a kid, as they say, I played around with these ICs, as we call them, and like 10 or 20 of these, and the connectors were only at the sides. Now with modern processors,
they fill the whole bottom.
Right, they have the whole bottom full of connectors.
Ball grid array, I think they are called, and then they are really somewhere melted onto the printed circuit board. It's amazing that all those points made good contacts there.
Yeah. So do you know if today's Pentiums are actually quite big? They are several centimeters in size, I guess, the whole chip. But the actual calculation unit, is it also as big, or are your chips that you build on your wafers, are they smaller? And the bigness of the chip comes from the fact that you have to put on all these macroscopic connectors to the rest of the world.
I think that the size of the housing is much more determining the size of the chip itself.
Yeah. Okay, good. So let's talk a little bit about wafer scanners. The purpose of them is to act as a projector to project the mask onto the wafer. Yeah,
we want to project a pattern on the mask. The mask itself is glass-like. It contains a chromium bottom layer. The chromium is actually the pattern that needs to be projected on the chips. Although the chips are very small, the magnification factor of the lens we use is only 4 times. So also the pattern on the reticle, the mask, is rather small. It's very detailed.
And is the lens making it smaller?
Yeah, it's making it smaller.
Okay. Yeah. So let's talk a little bit about the physical dimensions of these machines, because people probably don't have a good image of how these machines look. They're actually quite big, right?
Yeah, if you think on a regular beamer, as a lot of people have them, they are quite small and they are doing the same function.
Yes.
They have a mask inside, a projection optics, and they have a light source, and you project just on the wall. And we are thinking about a box of 30 centimeters maybe. Well, when you look to a wafer scanner, we want to demagnify to a factor of 4 only, and we are talking about a box of 5 meters by 3 meters by 2 meters. So 3 meters high and a floor space of 5 by 2 meters.
Okay.
The beast weighs about 15 to 20 tons.
And I guess they have to be mounted on a special foundation so that the truck that drives by the building doesn't disturb the production process and all this stuff.
Yeah, they are mounted indeed on a so-called pedestal in the clean room. But even then, we have some additional measures taken in order to isolate any vibrations from the outside world into our systems.
Yeah.
Well, because you want to illuminate a wafer, which is about 300 millimeters, and you want to achieve a accuracy in the order of nanometers. So, well, that is really something. Only the slightest disturbance will end up in a malfunctioning chip.
Right. So let's talk a bit about the different components that go into a wafer scanner. By the way, why is it called scanner and not wafer projector or something?
The very first systems were not even called wafer scanners, but wafer steppers, due to the nature how the image is projected on the system. Because then the mask and the substrate, the wafer, were put at a complete standstill, and then the light went on, and you had a new chip.
So it was a stepped process. That's why it was called wafer stepper.
Yep.
Okay.
And what we are doing now is that we are making the image of one chip while moving the mask and the substrate synchronously to each other. We really scan the image of the mask and project it on the substrate.
Why is that? Is it for a reason of throughput or?
The biggest reason of it is that when you make a wafer stepper, the image of the chip has to fit into the diameter of the lens.
The image of the chip of the wafer.
No,
the chip.
The image of the individual
of one chip. Yes,
has to fit physically into the size of the lens.
Yeah.
Well, if you want to make bigger chips, you have to buy a bigger lens, and a bigger lens is very much more expensive. So one way to avoid buying a bigger lens is to use only a strip of the lens, the largest strip that you can make over the lens, but very small in the other dimension. And then you can really draw your mask over this slit, as we call it, and then you can make a much larger image.
So in this case, you have the whole diameter of the lens as the biggest dimension you can have. And if you imagine to fit a square into a circular lens, then obviously the side sizes of the square are smaller than the diameter.
Yeah.
Probably
That
square root of something.
Yeah, definitely. And that is the reason that you want to do scanning.
Okay.
And it also averages out any imperfection in the lens, because you are using more of the lens to illuminate each individual spot. But that's probably getting a little bit too complex.
Yeah, it's hard to paint a picture without seeing something here.
Yeah.
So, okay, so let's go back to the different components within a wafer scanner. I guess from my perspective, we should probably start with the thing that holds the wafer, right?
Well, you could also start at the other end of the
light source.
The light source.
Yeah, sure. Okay, fine.
There is a relation between the wavelength of the light source and the dimension of the structure that you can illuminate, and it tends to use light sources with a decreasing wavelength. So we started with mercury lamps, and we got into excimer lasers, and for the next generation, where we use wavelength of 13 nanometers, we need to have some kind of a plasma source in order to get the proper wavelength out of it.
So you're using the laser not because it can be focused that well, where, laser pointer or cutting things where you put a lot of energy in a small area. You use the laser because it is all the same wavelength.
Yeah, and it should have a very constant wavelength and a very controllable wavelength. But it also should have some power, because unfortunately the light has to travel quite some distance, and has to pass quite some glass, so we lose a lot of the energy. The more energy we have at the wafer, the faster the illumination can take place.
So the light source itself is not part of your machine, right? It has basically a way where a glass tube, comes in where the light comes in, right?
Yeah, that's especially in that customers, they have special laser corridors, but that's also due to a safety measure, because those lasers use quite some gases which are not too healthy. So they are put
when they're in the production of the laser light. The laser light itself is not the problem.
No,
the production of them. Yeah.
The laser light has different properties like intensity and wavelength, and as we call it, it has a wavelength that is such that you cannot see it. It has an intensity that is such that once you saw it, you won't see anything again. So you should not look into the laser.
Yeah. Okay, and I guess you can also, if you have several wafer scanners in a production facility, you can have only one light source, which makes this also easier.
Well, that's not done. Indeed, we have one light source per wafer scanner.
Okay. Okay, I would have thought that they would centralize the light production and then use it for several machines, but okay.
Because the lens is the most expensive part of our system. You want to utilize it as much. So in the ideal situation, you would have 100% utilization of the lens, which means that you would need a light source for 100% of the time.
Well, but you could split the light, but okay, it doesn't matter. No, isn't done, finished. So the light source is the first ingredient kind of in the workings of a wafer scanner. So the light comes into the big machine, into the wafer scanner, and what happens then?
Well, you're going to condition this light so that the homogeneity of this light is optimized well, such that each spot gets the same amount of energy.
Mm-hmm.
Well, and there are other things being done in order to optimize for uniformity, and also polarization is taken into account. And
that's a bunch of lenses and filters.
Yeah, a lot of optics that pass through. And obviously we also some sensors, because we want to know the exact amount of energy that is entering our system.
Mm-hmm.
And then in the end, we're going to project the mask. So we end up with what we call, in fact, another word for mask is reticle.
Yeah, right.
And we have a subsystem called reticle stage, which is the mechanical device holding and moving the reticle over the lens through this stream of light.
So the light stream is kind of fixed, and then you're moving through the light, the reticle, as well as the wafer.
Yeah, we move it, as we say, through the slit of light.
Right.
And in order to avoid that, we illuminate pieces of the reticle that we don't want to be projected on the wafer. We have some masking blades, which determine the actual part of the reticle that gets illuminated, because sometimes when you are making very small chips, multiple images might be put on one reticle, and then it is very important that you illuminate the right image on the reticle.
Mm-hmm. So this is that you can switch which chip you produce by just illuminating different parts of the reticle instead of changing it, which is mechanically expensive.
Yeah. Okay. Well, in fact, not only that is expensive, but also the reticle itself is expensive. A lot of small structures need to be made on it.
How are those built, by the way? I mean, is this a manual process then, or is there other special machines?
There are other special machines. Okay. I think they are with some kind of an E-beam projection.
Mm-hmm.
They are etched on those reticles. And you might say, why wouldn't you make chips like that? Well, the throughput of such machines is too low to make a profitable chip production out of it.
In case you, the listener, speak or listen or can understand German, we've had an episode about nanostructures and surface modification not too long ago. And I guess some of these techniques are used to build the reticle.
That is, I can imagine,
Yeah. So the light passes through the reticle, and is this where the big expensive Carl Zeiss lenses have already been used, or are they used after that when you focus the light onto the...
Well, the biggest amount of money comes then. After the reticle has been passed, then we go through a lens, and you might think that magnifying by a factor of 0.25 or demagnifying by a factor of 4, well, that's not a big deal, but we are talking about a lens that has a height of 1 meter and a diameter of 60 or 70 centimeters.
It's a stack of lenses, not just one lens.
It's a lot of optics. Yeah. Because also in that place you want to manipulate some of the lens elements in certain directions.
Mm-hmm.
You want to have the best image out of it.
So let's step back. The reason why the lenses are so important and that's so expensive is because the projection has to be of an extremely good quality. You don't want any aberrations in it, right?
Definitely, yeah. And so any aberration will affect the position and the focus of the image that you are going to project. If you only make small deviations out of it, those contact points of your transistors won't contact anymore.
Yeah. So it probably means that if these lenses are 60, 70 centimeters in diameter, you only use a part of it for the actual light that's interesting. The rest is just to make the lens good.
Yeah, definitely, yeah.
Okay, so the light goes down through the lens and then it
should hit the substrate, but the substrate doesn't float by magic in the system, so we have a subsystem that's called wafer stage, which is holding this silicon disk, this wafer.
Mm-hmm. Okay.
Well, and it also has to move it, because we talked about it before, reticle and wafer are moved synchronously with each other in order to make the image.
How fast are they moved?
1 meter per second at reticle stage. Well, demagnification by a factor of 4, so 25 centimeters per second on wafer stage level.
Okay. And, I guess that's it.
That's it. So how hard can it be? Yeah, well, we are talking about moving kilograms of mass. And then, being able to control their position at nanometer scale.
Yeah. So let's talk a little bit about some of these challenges and how you solve them. When I was first in the ASML building, there were in the reception area, there is a very old machine from the 80s, maybe beginning of the 90s, when the movement of some of these things was hydraulic.
Yeah.
I can't imagine that that's how you do it today. So let's talk a little bit about how you make it so that you can do these high precision movements and high precision projections.
Indeed, you are right. The system that you are referring to is hydraulics. I think at that time it could obtain the required accuracy.
Sure, yeah.
But it must have been a problem with contamination of all this hydraulic fluid flying around because you might not see it, but on nanometer scale, definitely some particles must be coming out of it.
Yeah.
So that's not the way we are doing it now. We use linear motors, magnets, air bearings, and all those kind of stuff to have some mechanics moving.
I also understand that there is between the lens where the light comes out and the wafer, you have water these days.
Yep. And in fact, that's a technique that's also already very old because when they used to make microscopes in the Middle Ages, Antonie van Leeuwenhoek, they already discovered that when you put a drop of oil between the object you would want to see and the lens, that the image quality enhanced enormously.
Why is that?
Well, this is due to the diffraction properties of light from glass to air. It's different when you're going from glass to water, and it has some positive effects on your depth of focus, which makes your system more robust, more tolerant against any deviations into your focus behavior.
But on the other hand, you have to make sure that there aren't any air bubbles in the water. And you as you move your lens, or you don't move the lens, you move the wafer, but still there is something moving between where that's also a challenge, I guess.
Well, and the wafer is not flat in the end. So we have a lot of stacks on top of it, so it's a quite irregular surface. So indeed, you must be sure that no air bubbles are getting in. Because, they are magnification glass on their own.
Yeah.
And they will distort the image in a way that you don't have a working chip anymore. And that's not the only thing that's a challenge, but also being sure that no particles are loosened from the wafer and floating around into this water bath is one of the challenges. The photoresist should not dissolve into this water. And definitely you don't want to flood your system with the water. So you have to be careful to make sure that the water is only at the area below the lens. And that requires quite some engineering.
Are you allowed to talk about what you do, or is that secret?
I can say that the subsystem that is made for that is called the immersion hood, and several revisions of that immersion hood have been developed. We had to develop it fast, and they have certain regressions. Several versions of this immersion hood have been made, and still some research is going on that area in order to develop the best immersion hood that we can come up with.
Is that more experimentation, or is there any mathematics / physics / other science stuff you can actually calculate, or is that really just trying it out? And
for ASML, it was really a matter of research and experimentation because it was a technique that we didn't apply in the past, and we only were using optics, mechanics, but not that much fluid dynamics until that moment.
Yeah.
And it turned out, as within a lot of areas, that when you are going to work on it on a nanometer scale, there's not much prior experience with it on other fields. So we have to discover a lot of things ourselves.
Yeah. So you talked about the movement and the positioning, which is obviously critical. I know from my own playing around as a child with electronics that there are two ways how you can position something, either with a stepper motor and you count the steps, basically, and you know where you are, or you have a quote normal motor, but then you need something that measures the position and controls as a control loop, controls the position. You're doing the latter, right?
Yeah, we are doing the latter. We have very good servo engineers who developed this control loop, and we use quite some electronics in order to be able to process it. Control loops are characterized with a servo frequency and things like jitter and what we call I/O delay. Properties which determine how well we are capable of following the set point, as it is called. It's always a pressure. The servo engineers always want a faster control loop, and they also want to put more stuff in it, And we of the software department, we also have to fiddle with being able to do it in time. It's real-time embedded programming
Right.
At the top scale, I think.
We'll get back to that in a second, but how do you actually measure the position? Do you do that with, I guess, maybe another bunch of lasers that maybe,
we use interferometer-based positioning systems. And in this current system, we use a similar system, but then the laser beam is reduced in length. So we position them on a different space, and then by that we can even increase the accuracy of our system.
Mm-hmm. Okay, so let's talk a little bit about the software. I guess, as you say, there is basically an embedded control real-time system going on. You want to talk a little bit about that?
There's a lot of software into the system, and only the lowest layers are of this embedded part.
Mm-hmm.
Although I know most of that part because since the time I've been here, I've been working at the embedded software department. But I know there are, I think now, 25 or 30 million lines of code in our system, mostly C code, a little bit of Java, a little bit of Python. It's a layered architecture, and it goes from interacting with the fab automation system, the graphical user interface, all the calibration software, metrology software, and then going down to the embedded part where all the subsystems are located.
Just as a comment, metrology is not a sloppy pronunciation of meteorology, which is the weather stuff. Metrology is the science of measuring, right?
Exactly. Yeah.
Just to be sure.
Yeah. Although there are some meteorology-like aspects in our systems, like air pressure, and because that determines the accuracy on which you can measure the position. Because the air where the laser of the interferometer is passing through determines the quality of the received signal. You can imagine like driving on a highway on a summer's day, and you see this air vibrating
on a
in
hot
the end.
road.
Those kind of effects you want to prevent or avoid when you are measuring position.
This also kind of shows or illustrates how precise all of this stuff is.
Oh yeah, definitely. That's the reason why those areas where those beams are going through are very well conditioned.
You're working on a new class/family of machines. They're called EUV, right? So how are they different from the last one? What's the innovation this time?
EUV is an abbreviation for extreme UV. In fact, we already mentioned it briefly in the previous part when we talked about the wavelength. The current systems work with a laser which emits a light source with a wavelength of 193 nanometer. And in order to be able to project smaller structures, we have to cut down the wavelength to 13 nanometers, which brings us into the area of extreme UV. And we cannot use a regular excimer laser for that. We use a different light source which emits just this right wavelength. However, there is some problem with that kind of light, and that is that it's completely absorbed by most substances, even air. So in order to have some of that light on the wafer, we have to make the big part of our system in complete vacuum. Again, that's a technique which we did not handle in the previous systems.
This is actually really interesting. Again, when I saw this hydraulics thing first, you have been building the same kinds of machines for years now, for decades maybe even, but the challenges, the techniques you use, the engineering, the sciences that are involved, they change all the time. Now you have to deal with vacuum engineering, which you probably didn't do before.
Exactly, yes. And it's always good when you look to that developments that you realize again that the system, in principle, is the same as this beamer. You have a source of light, you have a projection system, the mask, and the substrate. So when you compare to software, the interface is more or less the same, but we are talking about a different implementation.
So I think people have heard about Moore's Law, which basically means that everything gets twice as fast or twice as small or twice as big in terms of memory every 18 to 24 months. Does this mean that you have to change the machines every 18 to 24 months? Is every Moore cycle, does it mean a different way of producing the chips, or is that not the case?
No, it's not, because then in that case we would, I think, have 30 of generations of systems. Well, we definitely did not make 30
So how often do you introduce a new approach?
When I started in 1998, we introduced the twin scan systems. Before that we had PAS systems, so that was a new generation. And I think now our EUV system is again a new generation. So from 1998 to 2010 is 12 years. So let's say every 10 years we really make a real new platform. Obviously there are many machine types derived from such a platform, but
sure, but they're not different in terms of the principle how they work, but rather in terms of size, throughput, maybe the speed is
well. And we put in a new upgraded version of the projection optics.
Right. Okay.
And that changes a little bit more faster. And that is also one of the drivers for being able to make smaller chips.
Okay. This sounds like a really a challenging environment to work with, because maybe not as a person, but at least as a company, you have to hire vacuum engineers or whatever you call these guys. I don't know what this is, what science this is.
Yeah, that's definitely true. What I like about this company, and I like it because obviously otherwise I wouldn't have been here for 12 years now, is that the principles can be explained in regular school. Every engineer here at ASML has a more or less basic understanding of the system.
Yeah.
However, when you really go to work at a subsystem, then you get to learn about a lot of details you never would have thought of.
Yeah.
And that is what I think makes it interesting to work here. And it's a highly dynamic organization over here, working in a very cyclic industry. So it gets from booming down to really, really bad times. And ASML is really focused on being able to survive into the downturns, as we call them, and really to succeed and to explode into those upturns. And in fact, we are in one of those upturns right now.
Okay.
And it's even that booming that they are asking guys from development to help out in production in order to make sure that we can produce sufficient systems. As it is now, obviously we are also recruiting a lot of people from various disciplines, software mechanics. If you really know your job and you really would want to work in the exciting environment, well, this is one.
Okay, so I guess people can contact your company through the website.
Yeah,
so this is the advertisement part of the show. I guess we put a link directly to the recruiting email address on the website.
Yeah, that would be nice indeed.
Yeah, no problem. Okay, so did we forget anything important? Or did we kind of cover it at that kind of level of detail?
I think we covered it more or less, If your heart is into technology, I wouldn't know any better spot to be than over here.
Yeah, it's very interdisciplinary.
Oh, yeah, term. Sure. Yeah.
Okay, then, well, thank you very much for being on the show.
Thank you, Markus, for giving me the opportunity to be here.
Sure, thanks. So that's it. I hope it was interesting, although it was a bit off topic. Well, I guess you could let us know whether you've liked it or not and want to hear more stuff like that in the future. We also thank Wilbert Albers and ASML for taking part in the discussion, and thank you for listening. Talk to you next time. Bye. Thanks for listening to Software Engineering Radio. SE Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons, or by talking about us on Twitter and Facebook. You can also support us by joining the team and shouldering some of the work. To contact the team, please send email to team@se-radio.net. Or, if your feedback is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under a Creative Commons 2.5 license. Please see the website for details.